Today, we are going to talk about the operators. This is the most interesting topic in MATLAB programming and can provide a new way of the MATLAB programming. Unfortunately, this topic is a bit tough, and you are able to understand this topic on the solely basis of the programming logic learned in the previous model, it's like a loop statement and selection statement. Thus, please review the previous topic carefully before starting this topic. When you use the operator in MATLAB, you can significantly shorten your code and reduce the number of the loop statements. Those scripts are like a math goal, so that's why I put this figure here. Okay? So at the end of these lectures, you can describe what is the vectorizing coding. Okay? And you can use the operators like numeric, relational, and logical operators when different combination of the scalar, vector, and matrix are involved. And you can redesign the loop-based script using vectorized code. Finally, you can apply this concept to solve the many different examples in previous model and the future model. MATLAB is optimized for operation involving the matrix and vectors. For instance, element-wise multiplications. We design the double loop statement and read and write the individual element between the two matrices, right? However, we can do this process by simply using the dot multiplication, right? For instance, the 2D matrix so if you multiply the element at the same location, we need to design the loop structure or the double loop structure. But to do this operation by simply using this dot multiplication, right? The dot operator. This is the good example of the vectorization. So rather than accessing the individual value using the loop structure, we can use this operator, these are the operator, to simplify this process. And also this process of this operator is already predefined in MATLAB. Okay? Vectorization is to revise the loop-based or scalar-based code. Scalar-based code means you can read the individual value using the loop structure to use the matrix and vector operation. That is called vectorization. Okay, this is one of a good example. Okay, why is it better? The script is much more readable. Okay, take a look at this code rather than let's say this one for 2 4 JJ 1 2 maybe this sorry, if this one become a C C I J J we need to do this process, right? This one is you are accessing the individual element, and then you assign the same location at the C matrix, right? So rather than this, we can simplify this operation using this by introducing this operator, right? Okay. So rather than this, this one is much more readable, right? So these are the less error prone. Okay, so To do the element-wise operation, you only need a one line, but in this case, you need to have 5 different lines. But imagine that you're switching this dimension by mistake. It is hard to find out this error if we take this structure, right? Okay. So if you vectorize your code, okay, you can reduce the risk of the mistake or some kind of error in your code. Okay. Finally, vectorization runs the code faster than the loop statement. Here's another example. If we try to design those operations in loop statement, we need to read the individual element in a vector and then compute this operation. It's a +3, right? And then assign this new value to the vector, right? So that's the basic process when we use the loop structure. However, MATLAB support this syntax that is called the scalar operation. Okay, MATLAB allows us to use this add operator. Okay, add operators between this vector and scalar. Okay, does it make sense? Okay, this is the vector, and 3 is a scalar, but MATLAB allows us to do the operation in this one, and then this process is already predefined in the MATLAB. What is the process? This add a scalar value of each element in a vector. Okay. So basically, we can easily understand these types of the script, right? That is the 7, right? Because this one is a similar syntax as the mathematical operation, the 3 + 4. What about this one? Okay, this syntax does not exist in the mathematics, but there is in the MATLAB. Okay, MATLAB predefined this operation. How? When you use the vector and scalars, MATLAB defined this operation as an element-wise operation with this scalar. Okay, this is the new syntax in the MATLAB. Okay, plus here is the operator. And this operation is already defined in MATLAB to do the element-wise the addition. Okay. Good. So actually we have learned several operators encompassing the basic numeric operator, plus, minus, multiplication, divider, or the logical operator, and relational operator, and dot operator. So all of them are operators, and then two values, A and B, are providing the left and right in the, here's the operator, okay, that produces some kind of other value. Okay, that's the important. Okay, it could be this numeric operator, it could be this relational operator, it could be the logical operator. Okay, so this value, sometimes it could become a scalar, sometimes it's a vector, sometimes it's a matrix, depending on the form of A and B and the operation. Okay, right? If you know scalar and this is a logical operator scalar, that produces a logical value, right? If you involve the matrix and the matrix, this is a matrix, and if you do dot multiplication, we will have the same size of the matrix in here, right? Understand that? You might be familiar with some syntaxes that looks like a math equation, so like a 3 plus 4, and this one is syntax is similar to the math equation. However, this is the programming script. MATLAB defined how to compute the resulting value using these operators when the different types or the size of the inputs are provided to the operator, right? Meaning that A and B could be the different types of scalar, vector and vector, and vector and scalar, and matrix of vector. There are lots of the combination by involving the different operation. MATLAB predefined those operations. Okay. I only show the limiting use of this operator between the specific variable types of the size in the previous module. For example, in the example of the equality here, this equality operator, so this operator is only used between the scalar and scalar, right? But MATLAB support that it can be used for scalar and vector, and vector and vector, and the matrix and the vectors. Okay, that's the predefined operation in MATLAB. Understand that? This module is to show what operations are conducted in the different types of the combination, and how we can use those operations and why they're useful. Okay, that's the objective of this module. Okay, let's start with what we learned so far. Scalar and scalar operations are very obvious, right? If you S1 is a scalar value, S2 are scalar value, we can do this numeric operation, right? 10, 2. Okay, we learn about in the module 2. Okay, we can do the operation between the vector and scalar, right? What is this operation? Element-wise operation. We can adding the scalar value to each element. Okay, so V1 is a 1, 2, 3, 4. We are adding the 10 each element, right? These are also similar. Okay, what about this one? This one also similar. Okay, element-wise operation of this matrix. Okay, does it make sense? Okay, here's the question. Okay, what about this caret operator? What is this value? That become 100, right? This is the 10 to the power of the 2, right? No. So 10 to the power of the 2, right? Okay. But what about this one? Okay, that's the element-wise operation, right? So here, vector 1 is a 1, 2, 3, 4. 2 means we do this operation, right? Okay. Okay. You can see the module 2. Okay. But what about this one? This one is not there. If there's no dot here, no dot, that is a matrix of power. Okay, that is not the element-wise operation. This one is interpreted as a V1 matrix multiplication of the V1 again. Okay. If S2 is become a 2, if S2 become a 3, we do this operation. Okay. So this operation is working? No. Why? Inner dimension is not matched. So V1 is a 1 by 4. Can you matrix multiplication is the 1 by 1, 1 by 4? No, because this inner dimensions are not matched, right? So basically this one is the matrix of power. Okay? So how about this one? S2 means M1 multiply M1. It's a matrix multiplication. In that case, M1 is a 2 by 2 square matrix. That's why it is working. Like this. Okay? Does it make sense? So I'll highlight that this one and this ones are totally different. Okay? Different. It's like this one and this ones are different. I already mentioned that, right? Okay. So how about the multiplication between the vector? That's the matrix, the multiplication. V1 is a 1 by 2, V2 is a 2 by 1. So it is working, right? It become a 1 by 1 scalar value. Okay. If we do this operation in the reverse order, V2 is a 2 by 1, V1 is a 1 by 2, the outcome is the 2 by 2. Okay. How about the M1 and V1? M1 is the 2 by 2, V1 is a 1 by 2. These inner dimensions are not matched. That's why there's a error. Okay. Does it make sense? Okay, good. We can use this sum operator as a plus operator. This multiply is a multiply operator between the matrix. Okay, if the dimensions are matched, right? This one is element-wise the summation. This one is the matrix multiplication. Okay, I already talk about this one. This one is the same with M1. Okay, does it make sense? I mean, this one is kind of the explain that we can use the different operator between the different forms of the combination. Matrix and matrix, a matrix, a scalar, and vector and matrix. Okay. Does it make sense? Okay. Okay. What is the backslash? This one. Okay, we saw this division backslash between the scalar and vector and matrix, right? For instance, V1 backslash, let's say 2 means you will get this one, right? It's kind of element-wise operation. But when we use the backslash between this matrix, that's the matrix division, not the numeric division. Okay? This one is identical with the multiplication of the inverse of your matrix. Okay? Okay, why? So let's think about the A multiply B equal to C. A become a C divided by the B, right? This one is kind of the numeric operation. Okay. What if we if these operations are matrix operation, these are the matrix multiplication. If you move the b in the right hand side, this become a backslash, right? So we call this one is the matrix division. This one is the same with inverse b. Y, a, b, inverse b, c, multiply inverse b. We multiply the inverse b in the both sides. This one become an identity matrix. A is a b, inverse b. That's why this one become a this one. Okay. There's no matrix operation in this course, so you don't have to, worry about the revisit this linear algebra in this course. But please keep in mind that do not use this division between the matrix. Okay, that is not the numeric division. If you want to do the numeric division, please use the dot division. Okay. I highlight this point several times, right? So dot multiplication is not the same with the multiplication. The dot's a caret is not the same with the caret, and dot division is not the same. So these are different. Okay. Make sense? Okay, good. What about the dot operation? As we'll already learn about this one is element-wise operation. Okay, there are two vectors having the same dimension. Okay, like the v1, v1. Okay, v1 and v2 transpose is the 2, 1, right? Okay, if there's the same dimension, we do the element-wise this operation. Okay. This one is the same as among the matrix M1 and M2 if they are same dimension. Okay. What about this caret? That caret, that is the element-wise the power of the S1. Okay. And this one is the matrix power, so this is not the same. Okay. Good. Okay, this is a real game. So we learn about this relational operator, right? But this operator is to compare the two scalar value and then saying the larger or less or the equal to or the not equal to. But we can use this operator between the vector and scalar. Okay, this is what we learn, right? Scalar and scalar. S1 is not the same, that's why it's a false, right? S1 is smaller than the S2, that's why it's a true, right? So we can use this same operator between the vector and scalar. Okay, this is not the scalar and scalar. How that work? This is also element-wise operation between the element in the vector or the matrix and this scalar. So here, this operation, so we do the element-wise operation. We compare with the S1 to the first element. That is the same. That's why it's a true. 1, 2 is not the same. 1, 3 not the same. 1, 4 not the same. That's why it's a 0. Okay. So this other operator is the same thing. V1 is smaller than or equal to S2. S2 is a 1, right? So V1 is this one is S2. S2 is the 2, right? So 1 is less than 2, right? 2 is equal to 2, that's why it's true, otherwise 0. Okay. Also, we can use this operator between the vector, and vector. Okay. To do this, the dimension between these two vectors should be same, so like an element-wise operation. The operation is also element-wise operation. Okay, they just compare the one by one at the value at the same location. For instance, here 1 1 is equal to, that's why it's true. These are not true, and the force value are the same, that's why it's true. Okay, the other operator is the only difference is that this operation is conducted between these two values. Okay, does it make sense? Okay, again, here v1 and v2 is our vector, right? If we use the operator between the vector and vector at the same size, that is the element-wise operation. Okay, does it make sense? So I would emphasize that this equality sign is not checking the equality of the v1 and v2. Okay, so this means is we already learned about the is equal, right? Not the same with the v1, v2. Okay, this one is element-wise operation. That's why the output from this operation is the same, the vector with the same size of the v1 or the v2. But this one is just a logical value, true or false. Okay. So don't be confused with these two. In this slide, I'll say this one is the output is the vector. Okay. Good. All right. Okay. We do this operation between the matrix and scalar. Okay. So previous case, these are the these are the vector, right? We can do the same operation with the matrix. You know, the operation is exactly the same as the matrix or the vector, right? If we put this one, we compare with the individual element in the matrix. Okay? 1 is 1, same. So the other elements are not the same. Okay, like this. Okay. Again, this equality check the element-wise. Element-wise. Equality check. Okay. And this 3 is the also the element-wise comparison. Okay. So this one is a similar. This one is a similar to that one. Okay. So here, this one is the compare the value at the same location. 1 and 1 is the same. Not same. Not same is the same. Okay. That's why you will get this one. Basically, the output is output size, so equal to input size. Okay, this is not logical value. Output is not logical value. Okay, Does it make sense? Okay, good. Okay. We can apply the logical operator between the different combination. Okay, we'll learn about this in the module 1, right? True and true is a true. True and false, false. True or false, true. False or true, true. True or true, true. False or false, right? That's the 4 different combination, right? That's the logical operation, right? Okay. Oh, this one as well. Not true is a false. Not false is a true, right? Does it make sense? Okay. So we can do this operation between the vector and vector and matrix and matrix. Okay. What about this one? V1, 1, 0. V2 is a 0 and 0. And only there's a difference. The only difference is that you need to use the single or an AND operator. Previous case in the between the scholars, we need to use a double AND and double OR. But if you're using this operator between the vector and matrix and matrix, it's like an array, more than one size. You need to use the single operator. Okay. So if you do this operation, 1 or 0 is a 1, right? 0 or 0 is a 0. That's why become this one. Okay. Matrix is also same thing. Okay. Let's take a look at this one. Let's do the AND operation. Okay. 1, 1, 1 and 1. True and true is a true. True and 0 false. False and false. 0 false and 1 is false. That's why become this one. Okay. Does it make sense? Okay, good. Okay, let's solve the couple of examples. This question is to write a script to count the number of 5 from a vector. The resulting count is assigned to the num5. Okay. So when you hear this question, you need to be prepared to write a script to solve this problem right away using the loop statement. Because set the loop range from the 1, 2, and vector is the size of the vector. Okay. Then read the individual value from a vector. Individual vector using the iterator. And then this value is a compare with a 5, right? If a condition statement, yes. And then increase the count, right? Okay. This is the script that we use the loop statement. How to solve this problem using the operator? We can directly check the equality using the equality operator between the vector and the scalar. Okay, here, so vector is the 1 by 9 vector. Okay, and then compare with a 5. Check the equality. Okay, that's why index vector become a 0, 0, 0, only 1 at the location of the 5. Okay, does it make sense? So once you get this index vectors, how can you get the number of the 5 value? We can simply sum this all element. like this. Okay, does it make sense? See, this one is how many line? 1, 2, 3, 4, 5, 6, 7, 8 line. This goes to 2 line, like this. Okay. Okay, we use the built-in function here. Okay, the bulls and cow problem again. I'm sure that you already knew this problem, right? Okay. So how to write a script to compute the bull? To remind our previous solution, we first make a single loop, and then set the range is 1 to 4 because there's a 4 value in each number, right? And then read a individual value, read a value from the x true and x test at the same location, same ith location. If they are the same value, we increasing the number of bulls. If not, we skip this action. Okay. Here the action is adding 1 to the number of bull. Okay. We already talked about this solution before, right? Okay. How to solve this problem using the operator? Okay. These x true and x test are the same size of vector. We actually, the operation is to compare the individual value at the same location, right? So we can directly use the equality operator between these two vectors. Okay. So we applied this equality operator between these two vectors. What is the outcome of the is the same? That is, this one is not equal 0, false. This is equal to 1, false, false, right? So how to compute the number of bull? We can simply adding all this value using sum. Okay. But here, this is the logical value, right? So when you apply the sum, this is a logical vector, right? Logical vector implicitly converted to the numeric vector like a 1, 0, 1, 1. Okay, that's why it become a 1. Okay, does it make sense? So when the two vector has the same size, this operator, this equality operator perform the equality check of the two number at the same location. Okay. So here's the tip. Rather than you define the is the same variable, we can directly put this your expression to here like this. Then you can solve this problem using only one line. That's cool, right? Good. Okay, now we will learn another indexing method. That is the logical indexing. Logical indexing is to index array using a logical vector. Logical vector. Okay. For instance, if you're accessing this vector values in vector 1 at the second and third location, we used this syntax. Okay. And this index vector is a numeric vector placed in the parentheses, right? However, this logical indexing is placing the logical vector. Okay, 1 means the reader and access the value. 0 are not doing anything. Okay, for instance, here. Oh, by the way, you can use any size of the logical vector smaller than the numbers of element in the target variable. In here is a 1 by 4. So size of the logical vector, the number of a value should be the less than 4. Okay. However, I highly recommend that you need to use the same size of the logical vectors of the target variable. Okay. In this case, please use a 1 by 4 logical vector. Okay. So let's see this example. So here, LG index, a logical index, become a 1, 0, 1, 0. Okay. And if you put this value to the vector 1, 1 is a reader value. This one is the reader value, right? Because of this one is expression part, right? Reader value, the first reader value 4, 0, 4. That's why so 4, 3 is assigned to V2. Okay. So go back to this same size of logical vectors. So we could write a script like let's say logical not good is the logical 101 and then V1 also become a 4, 3. This one is similar to this like just a regular so linear indexing. We can just access the value from the 1 to the end. 1 to the this location, the third location here. Okay, that's why you can steal the 4, 3. But again, I'm not recommend using the different size of the logical vector here. Okay, does it make sense? Okay, I repeat this process again. So logical indexing is use the logical vector as an index vector. So where is the index vector? So let's say V1. We put the logical indexing vector place here. We use just a numeric vector 2, 3 but this one is a linear indexing. The subscript indexing is we are using the 2 value with a comma, but this one is a linear indexing. Or we can accessing the multiple column, multiple row. We are using some kind of the numeric vector. Okay, rather than the numeric vectors, we can use the logical vector. Okay, logical vectors. So here, LG index is a logical vector. True, false, true, false. If you place this logical vector is the location of the index, we can read a value at the location of the 1. That's why we can read the 4, 3 here. Okay, make sense? Okay, good. One thing I forgot to tell you in advance is regarding this indexing is the linear indexing and the logical indexing. Your indexing vector is the row vector. Your output is the row vector. If your linear indexing and the logical indexing vector is a column vector, your output is a column vector. Here, let's say V2 is a row vector because the logical index this variable is the row vector. But if we use I would say V3 is equal to transpose, and then this become a column vector, the output become a 4, 3. Okay. I'll say this output vector, the size is the same with this logical vector. Okay. All right. Here's the example. Let's solve these 3 example. Before we start, as I said before, you should able to write its script using the loop and then selection statement. Okay. To solve the finding the numbers less than or equal to 10, we can apply to the kind of the relational operator. Okay. But in this case, without the loop, we can directly use this relational operator between the vector and scalar. Okay, let's see this example. Okay, if we execute this operation, what values are assigned to the ID 1? That is the here 1 is smaller than the 10, right? That's why it's a false. It's not larger than 10, that's why false. False, false, larger than or equal to, false. And this one is a 1, right? This one is a true. 0, 0, 1. Okay? Does it make sense? Basically, 1 is the this condition statement is a true, otherwise a 0, right? What about this one? Vector is not equal to 5. That's why all this 1 except for 5 location of the 5, right? Okay. What about ID 3? ID 3 is the, need a 2 condition statement, right? One is the vector is larger than 3. Vector is less than 3. That is the AND, right? So we need to use the, here's the mistake. That should be only 1 AND, right? Because these are the vector and vector operations. So ID 3 become a 1. Why? 4 is a place between the 3 and 7, right? 5 also the between 3 and 7. Other value is outside of this range. That's why the false 0 is assigned to here. But basically this 0 is a false here. These are the logical vector. Okay, this is not the numeric vector, this is a logical vector. Why? This relational operator produces a logical output. Okay, then this is the important part. We can directly use this index logical vector as an index vector. Okay, so here these are the index 1 vector. So if we plug in this index vector to the vector 1, it only reads the 1 location. That's why VQ1 become a 10, 11, because we read only the value at this location. What about the ID2? ID2 is this one, so we read all value except for 5, right? And ID3 the same. Okay, can you get this idea? This is the way of we can find the number or extract the number that satisfy this condition. Okay, it's pretty simple, right? So please compare this solution with the script using the loop and then condition statement in the previous model. then you will see the value of this vectorization. Here's another example. Write the script that extract the all odd numbers in vector 1 and assign a resulting vector to odd 1. Okay. Let's write this script using loop and condition statement. First, compute the number of elements named n vector here using the numel. Okay. Then you set the loop range 1 to n vector 1 here. Okay. Next, you read each value, right? Okay. The condition statements check if this your value is odd number or not. So what function do we use? It's a ramp function, right? It's a ramp function is set to if that number is equal to 1, that's the odd number, right? So if you plug in this number to the ramp function, if this condition is true, we are adding this value to the odd 1 vector. Okay. In this example, I didn't pre-allocate this odd 1 vector, and I just appending this new number to the odd 1 vector. Okay. This example is already in the previous model. Okay. How to perform this operation without using the loop statement? So there are 3 components here. Array as an input argument of built-in function. Second, logical operator applied to vector and scalar. Okay. And third one is the logical indexing. Okay. Let's see the one by one. As I told you before, most of the built-in functions support the array as an input, right? If you directly plug in all the vector into the ramp function and set to 2, it gives you the remainder. Okay. So here, vector 1 remainder is the remainder when each values are divided by the 2. That's why this one is a 1, 0, 0, 0, 1. All the odd number is set on the 1 remainder, right? Okay. By the way, what is the types of this vector 1 RAM? It's a row vector. What are the inside? Numeric value, not logical. Okay. So here, this one is a numeric value. It's a numeric 1. This is not saying the true and false, right? Does it make sense? That's why we need to do this operation to convert this one to the logical vector. So here, to check that this one is odd or the even, we are using this one. This one. Logical operation, equality operation between the vector, numeric vector, and 1. Okay. If your remainder is a 1, that is odd value, right? So we apply this concept. This concept is apply here, right? So concept here, and then we will get the logical vector here. Okay. Then once we get the logical vector, to extract this number, we directly putting this logical vector as an index location. Then we are extracting the value at the 1 location. Here, right? 1. That is the odd number. Does it make sense? Okay. This one is the beauty of the vectorization. Okay. Rather than accessing the individual value using the loop statement, we can do all operation with the vector or the matrix. Okay. In this case, by using the operator in built-in function, without using the loop, we can replicate this operation, right? That is the vectorization. Okay. Make sense? Okay, good.